We now discuss the solution of a problem from the section Real Analysis, and the problem is related to the convergent sequences. This question has appeared in the joint admission test for masters, that is JOM Mathematics 2022 examination. The given problem is, and it is the question number 6 in this paper. Let the sequence xn and sequence yn be sequences of real numbers defined by x1 is equal to 1, y1 is equal to 1 by 2, xn plus 1 is equal to xn plus yn by 2, and yn plus 1 is equal to under the square root of xn yn for all n belongs to n. Then which one of the following is true? We are given 4 options. Option A, the sequence xn is convergent but sequence yn is not convergent. Option B, sequence xn is not convergent but sequence yn is convergent. Option C, both the sequences sequence xn and sequence yn are convergent and limit n tends to infinity of xn is greater than limit n tends to infinity of yn. Option D, both the sequences, the sequence xn and sequence yn are convergent and limit n tends to infinity of xn is equal to limit n tends to infinity of yn. We are given 2 sequences, the sequence xn and sequence yn, and they are given as x1 is equal to 1, y1 is equal to 1 by 2, and xn plus 1 is equal to xn plus yn by 2, and yn plus 1 is equal to under the square root of xn into yn for all n belongs to n. Now we have to discuss the convergence of the sequences sequence xn and sequence yn. We now discuss the solution of the problem in detail. We have 2 sequences, sequence xn and sequence yn of real numbers. They are defined by x1 is equal to 1, y1 is equal to 1 by 2. The first terms of the sequence xn and yn are respectively 1 and half. Xn plus 1 is equal to xn plus yn by 2. That is the arithmetic mean of xn and yn, and yn plus 1 is equal to under the square root of xn yn. That is the geometric mean of xn yn for all n belongs to n. And we have by arithmetic geometric mean inequality, this is AM, arithmetic mean is always greater than or equal to the GM. So apply this here. So this will imply the arithmetic mean is xn plus yn by 2 is greater than or equal to geometric mean is under the square root of xn yn for all n belongs to n. Agreed. That means xn plus yn by 2 is given as xn plus 1 and greater than or equal to under the square root of xn yn is given as yn plus 1. That is, this implies xn plus 1 is greater than or equal to yn plus 1 for all n belongs to n. That means when n is equal to 1, x2 is greater than or equal to y2. When n is equal to 2, x3 is greater than or equal to y3, and so on and so forth. What about n is equal to 1? In the case of n is equal to 1, x1 is equal to 1, y1 is half. Therefore, x1 is greater than y1. So thus, xn is greater than or equal to yn for all n belongs to n. This includes now x1, y1 also because x1 greater than y1. Agreed. Now, xn plus 1 is equal to xn by 2 plus yn by 2. Agreed. Agreed. And for yn, we write yn is less than or equal to xn. yn less than or equal to xn, yn less than or equal to xn. So it will be xn by 2 plus xn by 2, that is equal to xn. That is, xn plus 1 is less than or equal to xn for all n belongs to n. That means this is monotonically decreasing sequence. This is monotonically decreasing sequence. Agreed. Now we will talk about the sequence yn also. Yn plus 1 is given to be under the square root of xn yn is greater than or equal to yn xn is greater than or equal to yn. So in the place of xn we write greater than or equal to under the square root of yn into yn, that is yn. That is, yn plus 1 greater than or equal to yn. This means the sequence yn is monotonically increasing sequence. This is monotonically increasing and xn is monotonically decreasing sequence. Agreed. So we have xn greater than or equal to yn for all n belongs to n, and we have seen the sequence xn is a monotonically decreasing sequence. The sequence yn is monotonically increasing sequence. So suppose we want to talk about the sequence xn, which is monotonically decreasing sequence. If we want to show that it is convergent, we have to see whether it is bounded above or bounded below. So if it is monotonically, now 1 by 2 is equal to y1, less than or equal to y2, less than or equal to etc., less than or equal to yn less than or equal to xn. So that means 1 by 2 is less than or equal to xn. That means 1 by 2 is less than or equal to xn for all n belongs to n. That means xn is bounded below by 1 by 2 because 1 by 2 less than or equal to xn for all n belongs to n. So xn is bounded below by 1 by 2. So therefore the sequence xn is convergent. Why? See, we use the theorem, every monotonically decreasing sequence which is bounded below is convergent. So xn, the sequence xn is a monotonically decreasing sequence now, and it is bounded below by 1 by 2. So therefore it is convergent. Using the theorem, every monotonically decreasing sequence which is bounded below is convergent. And for the case of yn, which is monotonically increasing sequence, if it is bounded above, then it is convergent. It is convergent. Let's see once again. Now 1 is equal to x1, yes. The first term of the series xn is 1. 1 is equal to x1. x1 greater than or equal to x2. x2 greater than or equal to xn. So etc. is greater than or equal to xn. Why? Xn is monotonically decreasing sequence. But xn is greater than or equal to yn. So for all n belongs to n. So that means you see this, yn is less than or equal to 1 for all n belongs to n. That means the sequence yn is bounded above by 1. And we use the theorem, every monotonically increasing sequence which is bounded above is convergent and converges to its least upper bound. So therefore the sequence yn is bounded above, and therefore yn is convergent. The sequence yn is convergent, and we are using the fact every monotonically increasing sequence which is bounded above is convergent. In this case it converges to the least upper bound. That's not required now. And in the case of a monotonically decreasing sequence which is bounded below is convergent and converges to its greatest lower bound. That is not required presently. So thus both xn, the sequence xn and sequence yn are convergent. Right. We continue in the next slide. So we have both the sequences, sequence xn and sequence yn are convergent. Let's look at our options. Option A says the sequence xn is convergent, but sequence yn is not convergent. And option B is sequence xn is not convergent, but sequence yn is convergent. But here we have shown that both of them are convergent. Therefore, both the options, option A and B, are not true. And in the case of C and D, both of them are convergent, but we have to look at the point of convergences, that is limit n tends to xn and limit n tends to yn. and if it is greater than, then option C is true. If it is equal, the option D is true. Now let us take, and both of them are convergent. Let the sequence xn converges to L and the sequence yn converges to M. So let limit n tends to infinity of xn is L and limit n tends to infinity of yn is M. Now we use the xn plus 1 is equal to xn plus yn by 2. This is the arithmetic mean. Now take the limits on both sides. Limit n tends to infinity of xn plus 1 is equal to limit n tends to infinity of xn plus yn by 2. And this is equal to limit of the sum is equal to sum of their limits you apply. And limit n tends to infinity of xn plus 1 is L is equal to 1 by 2 into limit of xn plus limit of yn. So limit n tends to xn is L, limit n tends to yn is M. So L is equal to 1 by 2 multiplied by in brackets L plus M. That will imply L is equal to M. That means they converge to the same limit. So thus both sequence xn and yn are convergent and converges to the same limit. That is limit n tends to infinity of xn is equal to limit n tends to infinity of yn. So look at your options. So thus the option D is true and option C is not true. So the answer to this question is option D. That is both the sequences are convergent and converges to the same limit. That is the detailed discussion of the solution of the problem from the section regular analysis, and the problem is related to the convergent sequences. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.